Cool. So recording started. Welcome to our Auger trainings. This is going to be extra exciting because Will, who's doing our training, he can't hear us, but we could hear him. So I guess that's the most important direction. So, but anyway, so this is the third training. So we had the Reads introduction Tuesday. Yesterday we did the outputs using the bouquet viewer tool, and today we're going to be focusing on the Auger module. This one is kind of a more in the weeds piece than the other ones were. So the Auger module is the portion of Reads that does the hourly calculations. So it's the one that does after Reads does a solve, it does an hourly dispatch and calculates a lot of our variability and other metrics. So that's what Will's going to be talking about. Will wrote almost all the code that's in Auger, so he's a good person for this. So he's quite the expert with all these things. So we're excited to have him share things with you. He's planning on not taking the full 2 hours. I think he said he's probably going to go a little over an hour. So we'll see where he actually ends up. We'll see if he's ready. We've got to communicate with him via chat. So
I can hear you now, Leslie.
Oh, you can hear us now? Oh,
I exited and I called in, and I have my phone audio, so we are all set.
Well, we're ready for you now, Will.
Cool. I'm just going to get one thing set up here. Sorry about the delay. Cool. And has the recording started?
Yep, it's already going.
Okay, awesome. All right. So as Wesley has likely mentioned, my name is Will Frazier. I have been responsible for most of Auger and the structure and things that reside inside it. So we're going to do this training today to hopefully make it a little easier for people to perhaps dig into Auger and work out any bugs they have, or at least have a better understanding of what's going on in there and why we have it, and how it works with reads. So first off, what is Auger? So an augur was a religious individual, a divine individual in ancient Rome, and these people were thought to be able to determine omens and predict the future based on the behavior patterns of birds. So these people would observe birds and their behavior patterns and make judgments based off of those. So since this module of Reads is attempting to see into the future what these different technologies and effects are gonna have within the optimization of Reads, we gave it this name, and we have a couple of submodules in Auger that we have named after birds. So the Auger then interprets the results of these submodules and determine some parameters that get fed back into Reads to inform the next set of investment decisions in the next solve year. So we have Osprey, which is a production cost model that we run at hourly resolution. And we also have Condor, which is a storage price taker model. So why is Auger needed? I'm sure that we've been through some of this within the past few days of Reads trainings, but just to provide a little bit of brief background, our aggregate time slice representation in Reads is insufficient for representing some certain components of the power sector if it's left unaddressed. But what we can do is we can take a deeper look at some of these effects that are only resolved when you look at a higher temporal resolution. And then we can use that to inform the model to make up for these insufficiencies. And the main pieces that we're concerned with here are one, the net load of the model. So here I have a plot of the hourly load and net load, and this is compared to the time slice level aggregations. So the dashed lines in each case are the hourly profiles, and the solid lines are how these are cast into our time slice level representation. I'm going to see if I can pull up a laser pointer here. Anyways, as you can see at the high end, when load's really high, our net load tends to be much lower than the actual hourly profiles, and same on the other side. So this causes some issues with assessing system reliability and accurately modeling prices and other things. So the energy prices are the other main piece that we try to address here. So here I'm showing our energy prices from the 2020 standard scenarios. This is in the mid case in the summer, and for each line we have a time of day, so our time slices are aggregated into morning, afternoon, evening, and night. And the difference in energy price between these time slices is generally quite small, often within 15% of each other, and 15% is what we assume for our round trip efficiency losses for storage. So in the absence of something else incentivizing the use of storage, the Reeds model would never see any opportunity for storage to operate based on the energy prices that come out of Reeds at the time slice level. So this is why we have Osprey and Condor, our models, and we do some interpretations off of that to inform some parameters that go back into Reeds for the next solve year. So what does Augur do? So as I mentioned, Osprey provides an hourly dispatch for the entire year. And so for each of our 134 regions in Reeds, they're all represented as a node, and all of our generation and load and hourly generation profiles from wind and PV go into this production cost model so that we can get this generation and transmission and storage dispatch. And we also get hourly energy prices out of this model as well. And we interpret those profiles for prices, generation, transmission, and storage to inform Reeds of what curtailment is and how that interacts with these other components, and also the value of storage operation based on these energy prices. And we also assess system reliability. And system reliability, we actually assess using 7 years of weather and load data and looking at the peak demand hours there. My neighbor is doing some construction. Wesley, is that noise too loud and annoying? Should I shut these windows? How are we doing there?
I don't hear anything.
You don't hear it? All right, cool. I'm going to plow forward. So the Reeds parameters that are populated by Augur, I have them grouped into these 3 main categories that we're informing Reeds. So we have curtailment, storage, and reliability. So all of these parameters for curtailment, they include curtailment from existing resources and marginal curtailment rates for investments in wind and PV, and how curtailment interacts with storage and transmission. And I have something on the next slide that will hopefully make this a little more clear. We also have a couple parameters for specific storage, including the hourly arbitrage value and the minimum operation that storage needs to meet in order to get that hourly arbitrage revenue. And also a few things on system reliability. So a little more simplified of how these actually fit into the Reeds model. So curtailment in Reeds is equal to curt-old, which is the curtailment from existing resources, plus the marginal curtailment rate for VRE investments times the amount of VRE investments we have. There's a curt-min-gen parameter that informs how much curtailment changes based on any changes in min-gen generation. So from retirements or new additions of thermal generators that have an InGen level. CURT store informs how additional storage charging, how much curtailment can be recovered from additional storage charging. CURT tran informs the same thing for transmission investments, and CURT prod is for H2 capacity investments. And a couple more nuances here. Curtailment reduction from transmission investments is limited by this really long parameter name. It's just the net load. Basically what this says is that if you're building transmission to send curtailment to a neighboring region, that neighboring region actually has to have load that needs to be served in order for that curtailment to be used to go meet that load. The min-gen level is formed by a parameter called rep-frac that comes out of Augur. We send the hourly arbitrage value for storage directly to the objective function. So the objective function is subtracted by this hourly arbitrage value based on the energy prices from Osprey multiplied by the amount of storage investments that Reeds determines is optimal. The variable storage in must be equal to or greater to storage in min, and storage in min is equal to the amount of storage charging that we see in Osprey in the hourly production cost model. So that storage is actually operating Reeds as much as we see in Osprey, and this hourly arbitrage value is supposedly more accurately represented there because we wouldn't want to give storage that value, but then not actually operate in Reeds because the price differential in the time slice at the time slice resolution is not great enough to incentivize storage operation. And the last couple of things here, the firm capacity of VRE is the sum of the existing VRE firm capacity, CC old, plus the marginal capacity credit rate times the number of investments. And our firm capacity of storage is limited by our SD bin size, our storage bin size. And there's more information on that elsewhere. Reach out to me if you're interested there. So how Augur actually integrates with Reeds. So Reeds, we typically run Reeds with a myopic sequential solve, which means we solve the 2020 system, and then we move on, we move ahead in time, say to 2022, we optimize investments there, and so forth. But in between those Reeds optimizations, there's this little file here in the Reeds folder, the Augur data dump, which dumps the information from that investment year out into a GDX file, which is read in by Augur, and Augur does its thing and writes out the 14 parameters that I just covered into a GDX file, which is ingested back into Reeds, and those parameters are used to inform the next solve year's investment decisions. Taking a deeper look inside Augur for the moment, it has a similar sort of sequential structure. So the first thing we do is we format the data from Reeds so that it can be used in these other scripts downstream. The next thing we do is we run Osprey. So this performs our hourly dispatch of generation, storage, and transmission. This is so we have a file for running the actual model, and then another file is going to dump out a bunch of CSV files that are going to be ingested by Augur. So those results can be interpreted later on. The next thing we do is we determine all of the parameters relevant to curtailment. So this is looking at those Osprey results to calculate how much curtailment exists and how curtailment is going to interact with marginal amounts of transmission, storage, and other things. From there, we go to Condor, where we run our price taker model using the energy prices out of Osprey to determine the value of energy time shifting for storage. And finally, we determine the contributions of storage and VRE to system reliability, looking at net load across 7 years of data. So I'm going to do a quick aside here. Within Augur, we have, just give me 1 second to log on to a remote machine here. So within Augur, we use object-oriented programming in Python. So we have class structures to handle all of the data in a structured and organized way. So I'm just going to go through a quick example of how to use classes in Python.
Wait, Will, question. So this is, so just want you to highlight here. So this object-oriented piece, a lot of it has come into the 2021 version that's not yet public yet. Can you just talk real quick about that and how the version that's out there right now and the version you're talking about with the object-oriented interact here?
Yeah, sure. So Augur was first introduced in the 2020 version of Reads, which is the open source version that's available right now. I'm new to this type of programming, so when we first wrote Augur a year ago, it was we used Python largely as a scripting language, and we had these long sequential scripts that had some suboptimal methods for handling data and for passing that data around. So it was difficult to make changes in Augur in the 2020 version of Reads because these scripts were rather inflexible. So for the 2021 version of Reads, I went through and tried to implement a better structure for Augur using classes and object-oriented programming in Python. This is the first large thing I have built using this type of programming. So if there is anyone that does work on the model who is savvy with this kind of thing and has any suggestions for improvement or that type of thing, once the open source version of the 2021 Reads model is available, I would welcome your input. But yeah, most of what I'm going to go through now at this point, where I talk a little more in depth about the code of Augur and how it works and how it interacts with Reads in more detail. And I'm also going to go through an example of opening up Augur and trying to debug something. This is all applicable to the 2020 version of Reads, which I think, Leslie, is going to be released in October publicly.
That's how it comes out with standard scenarios, which is targeted for October.
Okay. Okay. So with that caveat, I'm going to move forward with a quick example here about object-oriented programming. So the basic gist of it is that you can create a class in Python, and a class in Python is going to represent a certain structure or a certain set of a thing that you want to be able to represent in your code. So my example here is I've created a nice example called pet. So we have this class called pet, and the class pet has attributes, name, and tricks. So if I'm going to use this interactively. So here's my class pet. We're going to create this class, and then I can create a pet called my pet, and it's going to be an instance of the class pet, and I need to send it a name. So this init function, or method rather, this init method of the class pet is called automatically when you initiate an instance of the class pet. So here I'm creating an instance of the class pet. This instance is called my pet, and I'm going to pass it the name Ted. So now I have an instance of the class pet called my pet. So if I look at mypet.name, it's going to tell me that my pet's name is Ted. So this self thing is generally pretty confusing for most people when they're new to Python. What self means is that within a class, if you have a method of a class, the first argument of that method is always the instance of the class itself. So when I call the class pet, the first argument that gets sent is actually my pet. And then the second argument is the name of my pet, which is Ted. And when this instance of pet is initiated, it assigns the name that I gave it to be the name. So this attribute of my pet, the name is now Ted, and my pet, Ted, at this point does not know any tricks, right? So if we want to get, oh no, there we go, okay. So we can get a little more in depth with this and use the hierarchical structure of Python to create what's known as a subclass. So the first subclass we're going to talk about here is dog, right? And so now a subclass inherits all of the information, all of the properties from its parent class. So this class dog is a subclass of pet. Pet is the parent class of dog. And so now dog inherits this init function. So anytime I create an instance of the class dog, it's going to initialize it the same way it would for any pet, except I can specify some additional things for my dog here. For example, I can say the max number of tricks that any dog can learn is 3. So this is what's called a class variable. This class variable applies to all instances of the class dog. And I've also given dog another method called learn tricks. So this method will teach the dog a new trick. So it's the arguments for this method are first self, so whatever the instance of the class that's calling this method, that instance itself will be the first argument, and then the next argument will be the trick that you want to teach it. And so this method will check to see if the length of its attribute tricks is longer than the max number of tricks it can know. And if it's not, it will append that trick to its attribute tricks, which is right now an empty list. And if it is longer than that, it'll say the maximum number of tricks has been reached, cannot learn any more tricks. So let me go ahead and grab my class dog here, and we can, now we're going to say my pet equals dog and Ted. So now I have my pet dot name once again is Ted, and let's just say my pet dot learn trick. The first trick we're going to teach Ted is to sit, right? And so now if we look at my pet dot, oops, my pet dot tricks, that's going to return a list which now includes sit because we've added sit to that attribute there. So next trick I want to teach Ted. So this is Ted. As you can see, Ted has some boundary issues, right? So let's say it's early in the morning. You're going to take Ted for a walk, and you're trying to put on your shoes. And Ted's really excited. He wants to go on a walk. He's excited to see you. It's the morning. So he's all up in your business, and so then a really good, important trick to teach Ted is going to be to back up, right? So let's teach Ted another trick. Learn trick, back up. And how about shake? Shake is another fun trick. Shake. So now Ted has a set of tricks that he knows. Oops. Sit, back up, and shake. And if I tried to teach Ted any additional tricks, it's not going to let me because let's say roll over. Maximum number of tricks for Ted has been reached. Ted cannot learn any more tricks. So that's a quick look at how different attributes and methods can work. I'm waiting for this top bar to go away so that I can move this away so I can get back to my presentation here. So this is really useful because if there's another sort of pet that we want to include, let's say we want to include a cat in our file now. We want to be able to model both dogs and cats. We want to do it efficiently. So I'm going to create another subclass of pet called cat. But obviously cats are very different than dogs. So I'm going to have to redefine this learn trick method for cats so that it's different than dogs. So that when we call learn trick for any instance of the class cat, it's just going to say, this cat has no interest in learning the trick. General mayhem will ensue, followed by incessant fur licking. And we've also changed the init function here so that whenever we initiate an instance of the class cat, what it will do is this super method is actually a native method of Python, a native method of the native class object in Python. So anytime you create a class in Python, it's actually a subclass of Python's native object class, which has this super method, which what you can do with this is when I call super init, it will actually call this method of the parent class. So whenever any instance of cat is created, first it's going to call this, and it's going to set these values for the attributes of cat. And then when we get here, it's going to amend that, and it's going to change the tricks for cat. And the two tricks that cats can know in this case are to lick fur incessantly and cause general mayhem. So once again, if I go back here and I can grab my class cat, and both are subclasses of the class pet. What have I done here?
Deleted the last line of your class dog.
Oh, did I? Oh, I did. Thank you. Thank you, Wesley. So let's create this class. And now I can say my cat is cat. Let's call him Benjamin. And the cat, his tricks are lick fur incessantly and cause general mayhem. And I am not able to teach this cat any tricks because Benjamin is not interested in sitting. So this, and once again, I'm just waiting for this to go away so I can move this out of the way and get back to the presentation. This allows us to use a hierarchical structure for similar types of data to organize things well. And then we could, if we really want, we could create another subclass of the class dog. Now I have a class Australian Shepherd down here, which is just like a dog. Australian Shepherds are just like any other dogs, except they can learn more tricks. So I have changed the class variable max tricks to be 8 for Australian Shepherds, rather than 3 for any other kind of dog. So a quick review here, because I'm going to be using these terms class, subclass, class variable, attribute, method, and instance. So the class, for example, a pet, defines a common set of characteristics for something you want to represent. A subclass will inherit all of the properties of the parent class unless they are changed or overwritten. A class variable, which in in this example, I used max tricks, defines a characteristic for all instances of a class, whereas an attribute defines a characteristic for a single instance of that class. So if I were to create another dog, you know, and name it Fido, Fido and Ted would both have max tricks equal to 3, but their name attribute would be different, where Ted's name is Ted and Fido's name is Fido. A method is basically just a function that can be performed by an instance of a class on that instance of that class. And an instance is just a single use case of a class. So within Augur, and I wish I could do this. Okay. So within Augur, I'm going to go ahead and pull this over, and we can take a look at this. So in reads, there is a reads Augur folder. And within this folder, there's a utility folder. And this utility folder contains a lot of meat of what's actually happening in Augur. So we have a functions, generator data, hourly profiles, inputs, and switch settings. So in our generator data file, this defines a class for all generator technology types. And as we'll see later, all generator technology types are subclasses of the parent class for all generator technologies, which I believe is called tech types. And so we use this hierarchical structure of generator types so that we can easily handle the data between these and define new technology types and data rather easily. In case, you know, there's a new technology you wanted to add to reads, then you could just come into Augur and create a new subclass rather easily in generator data, and it should propagate through the rest of Augur quite easily. And I'll talk about gen data and gen text a little bit later, which are dictionaries that are defined in this script. Similar thing in hourly profiles, so we handle all of our hourly data in this hourly profiles Python file, which again uses a hierarchical structure to define the different ways that our data is stored and manipulated and those types of things. So we have hourly profiles, and Augur results are defined here. Switch settings defines a class called switch settings, and this class is the parent class for all classes that are used in Augur. And this allows for the switches to be seen by all classes. So logic based on whatever switch is used in reads can be applied easily and consistently across all of the data in Augur. Inputs is another file which is used to read in all of the data in an organized and consistent fashion. So I'll go through that a little bit later as well. And we also have functions, which just houses additional functions that are used elsewhere, but not necessarily specific to any class. They're not class methods. Okay, so the data flow between reads and Augur. So the switches from reads get into Augur via 3 places. The first is a cases.csv file. The second is command line arguments, and the third is value defaults.csv. So when you do a reads run, and I'm sure that we have looked at a cases file previously. So we have all these switches that are defined and go into reads and you know, define how certain things are handled in reads. Some of these are relevant in Augur, some of them are not. But for completeness, we send all of these switches to Augur. So I'm going to open this switch settings.py file first. So here's our class switch settings. it has a few class variables, and then it has a few attributes, right? Its attributes are, one, the GDX file where we're going to get all of the data from the previous read solve year. The next and previous years that were solved in reads, the name of the scenario, and then the last one here, the important one, is this switches attribute, which is a dictionary. And in this dictionary will include all of the switches from this cases file, as well as the next year and previous year and scenario name, which are passed directly to our Augur via command line arguments. And also inside Augur, there is this additional value defaults CSV file. And this just includes some default values that are used in Augur because we didn't want to hard code certain things. So these are the three places where switches will come into Augur from: the cases file, the command line, and the value defaults CSV file. The data for Augur comes primarily from two places. It comes from the reads data GDX file. So as I mentioned previously, after reads solve year finishes, it's going to call that D3 Augur data dump file, and it's going to dump out all of the relevant data for Augur into a GDX file that can be read into Augur and used. Also, some of the inputs come from CSV files inside the inputs case folder when you do a reads run. And all of these are read in via this inputs.py file in the utility folder. So I'll pull that up really quick. Inputs.py has this first class Augur input, which again is a subclass of the parent class switch settings, so that the switches can be used when data is being read into Augur. And so the primary method for this Augur input class is get data. So when we get data, it will read the data in and perform, a few things to make sure, everything is consistent. For example, we drop all regions that are not included in your solve. So if you're only solving ERCOT, for example, and you read in data that has data for the entire US, it will drop all of the regions that are not included in ERCOT. Couple other relevant things. Let's say you're running with the cooling water switch on, and you're reading in data that doesn't have the cooling text defined for that. This will look and check that switch, and if that switch is activated, it will go to this other method so that you can map the cooling water text onto whatever you're reading in. So it's important for all of the data in Augur to be self-consistent, and so that's why whenever anything is read into Augur, it all comes through this same class method, get data here, so that everything is self-consistent, and Augur doesn't break when you add anything new into it. This read data method is defined in some of these subclasses, which depend on the actual file format of whatever your input is. So if your input's coming from a CSV file, it's going to call the read CSV function. If you're reading from the GDX file, it's going to use the GDX pandas class to read that in. All of these inputs are defined in this dictionary here at the bottom. So this dictionary inputs houses all of the inputs that get read into Augur and used. And each key in this dictionary points to an instance that gets created of whatever class that the certain input belongs in. So available capacity comes from reads, which is in the GDX file that's spit out by D3 Auger data dump. And a couple of these are the arguments that are needed whenever you initiate an instance of the GDX input class, which is a subclass of this Auger input class. So if we go to this GDX input class, we'll see that when we initiate anything, it needs a key. So the key is going to point to the name of the parameter within the GDX file. And then this call names is a list of names for the different columns in this file. And there's also this attribute df, which we initialize to be none. And so when we read in the data, the first thing it does when it reads the data is it checks to see if the data frame is none. And if it is, then it will grab the data from that GDX file and return that data. And so if, for example, we wanted available capacity and we call inputs avail cap, and it sees that its attribute df is none, then it's going to grab the data and it's going to set the attribute self.df equal to the data when it grabs it. Then later on in Augur, if we call that again, if we call inputs avail cap get data one more time, this will see that we've already grabbed the data once, so we don't need to read it in again. And this saves some time for us when we're reading in large amounts of data. So it can seem a little cumbersome to use something like this, so that whenever you need to add a new input into Augur, you have to come in here to the inputs data frame and add it in correctly and assign it to the proper class. But using this allows Augur to be quite flexible and easy to augment and integrate as reads changes, because we're always updating how reads works and the different capabilities that reads has. And so in order to keep Augur up to date with that, it's important to have a nice consistent structure that we can use so that the two are easy to keep in sync. So I'm going to go back to my presentation here as soon as this top bar goes away and lets me move the screen. So just give me 1 second. There we go. Okay, so we've gone through switch settings and inputs. Next, we're going to talk a little bit more about these dictionaries. So we went through the inputs dictionary, which is a dictionary, and each key in that dictionary points to an instance of a class that defines a specific input property. We have a set of 5 of these dictionaries that are used commonly throughout Augur. All of these dictionaries are written as all caps. Whenever you see something written in all caps, you know it's one of these main dictionaries that are used. Gentext is a dictionary, and each key in the dictionary gentext points to an instance of a class for each technology group, and attributes of these instances are data frames defining certain properties of that generator, and methods of each of these subclasses define the different ways of how we're going to set the data up. Gendata is a dictionary of data frames, which basically just collects all of the attributes from each of the different technologies and packages them into a single data frame that can be used. Hourly profiles has each key defines a different profile that's used. So we have load profiles, we have VRE capacity factor profiles, we have other things. Osprey results houses all of the profiles that come out of Osprey. So we have transmission profiles for each region. We have net transmission. We have generation profiles, hourly generation profiles, hourly price profiles, that type of thing. are included in this dictionary. And we'll get into all this in a little more detail, not a ton of detail, but at least to give people a general overview of how things work. So as I mentioned, gentext, so here's our gentext dictionary, which is defined in utility/generator.py, generator-data.py. And each key for gentext defines a different class. So we have this parent class for all generators, tech data, and tech data has a class variable called min-gen size, and this is defined because generators smaller than this are not considered in Augur or in Osprey. So anything less than 5 megawatts is dropped and not included in Osprey. So this is our class variable for tech data. We also have all of these attributes for every instance of the class. And these attributes are the different properties that are relevant for these generators in Augur. So we have available capacity, daily energy budget, which, let me go back. Daily energy budget is used for dispatchable hydro and certain other hybrid energy technologies in Osprey, energy capacity for storage, generator cost, hourly capacity factors for wind and PV, max capacity, min-gen, those sorts of things. So if I come over here and let's go to generator data and just look at a couple quick examples. So down here at the bottom is where we have gentext defined. And I'm going to zoom in a little bit because I think this may be kind of small on the screen share. Once again, generator data defines a class instance for each of these different technology types. So if we go back up to tech data here at the top, we see our definition of the tech data class, which again is a subset of switch settings so that we can have access to all the switches and reads whenever we're formatting the data for any of these technologies. Let's look at, for example, format gen cost. So generation cost is the fuel cost plus the VO&M, and this applies to nearly all generators. So we have this defined at the top here within the tech data class. So that the first thing it does is it calls a method of whatever object is being manipulated here, calc fuel cost. So this is going to call a different method here and calculate the fuel cost, which gets the fuel price, and then multiplies that by the heat rate. So we get the fuel price, we get the heat rate, multiply the two together. Get fuel price is its own method because some of the technologies in reads have their fuel prices determined in different ways. For example, we have a supply curve for natural gas, and the price of natural gas is determined endogenously by reads based on natural gas demand. Whereas for other things like coal, we have coal and nuclear, we have a fixed price. So if we, this method will grab the fuel price that's specific to that specific class. So once we have the fuel cost, then we get the VOM cost, and we filter for the technology and add those two together. So this filter tech is perhaps another key one that's good to go through here. So what this is going to do is for once an input is read in, this will filter on that technology's specific that technology class's tech definition. So I use technology like 10 times in a row, so I'll try and be a little more explicit here and explain that better. So the tech data class has this attribute tech key, And the tech key is the one argument that's required whenever you're initiating an instance of the tech data class. So if you notice down here at the bottom, when we created all of these instances of that class, so for battery, for example, when we set battery, when we point battery to an instance of the storage data class and pass it the tech key battery, it knows that one, the GenTech battery is an instance of the storage data class, and also its tech key is battery. So when it filters any of the data in when we're manipulating this particular object, it will filter for all of the technologies that are included in battery. And maybe we can go into that a little more later. Basically, there's a lot of data manipulation here, set up in such a way that things are generic here at the top, and for different technologies that have specific that need specific methods. For example, natural gas. If we go to natural gas data, it's a subclass of tech data, and it just has a couple of properties that it needs to handle specific to natural gas. So we have changed the get fuel price method to grab the natural gas price from our inputs dictionary, and also the calc fuel costs is slightly different for natural gas relative to other technologies. So that's defined here. I'm going to go back to my presentation here. So moving forward just a little more, so in APREP data, which, as I mentioned, is the first script that is called when we run Augur, so that it can format all the data and send it to Osprey and the other scripts downstream that use the data. This little block of code here really encompasses like the meat of what's going on there. So for every tech in GenText, so this is for each key in GenText, and then for each key in GenData. So as I mentioned, GenData is a dictionary with a data frame that includes the properties for every technology instead of just a single GenTech. We're going to get the data and append it to GenData in this sense. So when we call when we call the method prep data and give it the key, which is the different data that we're trying to format, it's going to go to this prep data method in generator data. This is a method of the tech data class. And depending on the key, it's going to call the different methods so that the data can be formatted properly and appended to whatever dictionary here is relevant. And I think at this point, it may be most useful to just walk through Augur the way I usually do it. So when I am using Augur, I typically use an IDE. My preferred one is Spider, as we've seen before where we had the pets example. So if I have a reads run, I can pull the augur.py file out of my run folder. And I'm going to drag it here into Spider. And then I'm going to set my directory to be in that run folder, which I believe we used July 28. Hi, RE, that's not the one we wanted. We want this Augur test one. Excuse me for just 1 second. Okay. So we have our auger.py file, which is the driving script for all of Auger. I set my working directory to be that run folder. This way, when I get to the first bit here and I start importing things, it knows to go into this reads Auger folder, and it's going to grab from aprep data, it's going to grab everything that we need. And it's going to go into the utility folder and grab switch settings, and it's also going to grab all of these dictionaries that I mentioned before. So this is the main function in Auger. 3 arguments are passed to it: the next year, the previous year, and the scenario. There's some logging information here, and then we call the function reads Auger, which exists here at the top. So in my reads Auger function, this is the actual procedure of most of what's happening in Auger, or of all of what's happening in Auger. So here there's a little note here to debug, uncomment these lines, and update sen, as well as the run path. So I want to run Auger, and I want to run it for my next year is 2024, my previous year is going to be 2022. This is going to grab the base name from my working directory, which is the scenario name. And the first thing that's going to happen is we're going to call the set switches method from this switch settings class that we talked about earlier. So we're going to define all the switches first off. So once these switches are defined, then we can move forward and start going through Auger. So the first thing we do is we prep the data for Osprey. This includes hourly profiles and generator data. So this prep data function was imported from our aprep data file. So I'll pull that up here so we can take a look at that. The first thing it's going to do is it's going to define a marginal step size for wind and PV. We need a marginal step size for wind and PV to determine things like the marginal capacity credit. And that is based on the amount of investments that occurred in reads during the previous solve year. We're going to go through this format profiles method for every profile that exists in our hourly profiles dictionary, which is in our hourly profiles Python file. So just like any of those other dictionaries, we have hourly profiles, and for each key in hourly profiles, we have an instance of the class here in this script. So I'm going to go ahead and go through aprep data here a little bit slowly. So here's our prep data function, which is called by the Auger file to get these reads inputs, and also in prep data at the end of it, we're going to write out some CSV files as well as a GDX file that are going to be read into Osprey. So the first thing we can do is we can set our marginal VRE step size. We're going to format our hourly profiles. So this is also what I would be doing if I were to, if there is an error in Auger, for example. I happened to run this test yesterday because I knew an error was going to occur. If an error does occur in Auger, it's in this list files folder. It's going to spit out an Auger errors file for the next solve year. and it's going to tell you, here it's going to give you a traceback of what the error was. Typically, not a lot in Augur is changing other than the way data is read in and formatted so that it's constantly being updated with reads. So if there is an error in Augur, it's typically going to be on this front end, and I will go through how I would go about finding this error and debugging this. So we see that this is in this prep data function. There's another function that's being called down here, format prod load, and then inside format prod load, we're getting some sort of error. So we're going to find out what that is as we step through a prep data here. So I have, we'll just do a couple more class examples here. So when I look at gentext, right, gentext is a dictionary, so it has a key for each of these technology types. And each of these is pointing to utility generator data, storage data. So battery is an instance of this storage data class, as well as the rest of these. So if I look at gentext battery, now this is going to be just my instance of that storage class. And if I remember that my attributes for battery are the different properties that battery can have. For example, max cap, when this class was initiated, the attribute max cap was set to none, right? But once I run this bit of code to populate all of the data, then we're going to be able to see we're going to see that the attributes for all of these classes are then going to be populated with data frames. So now when I go to gentext battery max cap, now I have a data frame with all of my capacity from reads. And you could also look at energy cap, which is going to be in megawatt hours, the energy capacity for each of these same generators. So just for a quick example, if I look at my storage data class, storage data is going to have a format energy cap method. And what this format energy cap method is going to do is it's going to grab the max capacity, and then it's going to get the storage duration and then multiply the max capacity by the duration and set that to be a data frame as its energy cap method. So that's happening for all of the data in Augur, all of the generation costs, capacities, capacity factors, that type of thing. There's some additional data formatting done down here for Osprey. We're not going to go through all of this because there is quite a bit happening here. But we are going to notice once I get to this line, then we're going to run into our bug, right? So this is our key error that we saw earlier in our error file. So this is in format prod load. So I'm going to come into my reads Auger folder and go into my utility folder. Functions.py is where format prod load lives. So let's find, first, before we do anything, let's import everything at the top of this script. And now we're going to look for format prod cap. We're going to scroll down to format prod load. So we're reading in a few inputs here at the top. And then this I'm going to check this if statement. And I see that it is true, so I know we're coming inside this block of text here on this conditional. And I believe it was this line here where the error is kind of, okay, probably not this one. I thought I had. Oops. So get prop is actually a function here. That's why it's not defined. So I'm just going to define all these very quickly so that we can get back to this. On that prod load. I believe this is the line where we were having the error, so I'm going to do everything up to that point. Okay, let's keep marching through. So here's our error. Our key error is megawatt. So we're trying to divide this megawatt hour column and consflex by the hour column. And I see that the issue is that the megawatt hour column doesn't exist, right? And that's because there's no data here. We've run into a few errors with Augur early on here, where empty data frames tend to cause issues. So what I'm going to do to get around this one is consflex is coming from this consumption data frame. So I'm actually going to move this outside of the block here. And I'm going to add another conditional. And say not consumption dot empty. And so now we're only going to go into this block of code if there's actually data that exists in consumption. So I'm just going to run this entire function to see, just to double check, to make sure that my fix worked, and my fix did work. Let's check on consflex and consnoflex just to make sure. So consflex has our day, our region, and our megawatt hour. It's empty, and then consnoflex is actually going to be a set of profiles for each region where we have our inflexible H2 demand is actually what this is. So I would save this change, and then now I've fixed my bug in Augur, so I could come back and either restart the console here and just run it again just to make sure it works, and then go through pushing the change and whatever else you would need to do to get Augur working. So I realize that I have covered a ton of material, and some people may or may not be familiar with classes. If you are, hopefully this was at least a little bit helpful. If you're not, hopefully this wasn't too much information to process. And I think at this point, I will open it up for questions. If anybody has anything, I'm happy to go through anything. I do think we have some time left in the webinar here. And if not, I'm happy to end it early and people can just refer to this recording. Hopefully it's helpful later on.
So, yeah, just a quick question in the chat. Will, could you explain the notation, the and followed by the slash when you have the multiple lines for the if statement?
Yeah, sure. So this backslash in Python just means I'm going to continue my my line on the next, I'm going to continue this line of code on the next line here. And all the and does is it makes this conditional depend not just on this condition, but also on this condition. And since I have another and here, it's also on this condition, right? So I can say, you know, if true, print yes. And so it's going to print yes. And then if I say if true and false, print yes. And so now, since I have the false condition in addition to my true condition, it's not going to print it. Similarly, I could use or here, if true or false. One of these two is true, and so then the condition is true, and it's going to perform the operation.
Okay, thanks, Will. No, I think that's everything. So yeah, so this recording is going to be available, so you get to come back and check on it. And just as a reminder, you can follow up with on the discussion page if you have questions or comments there. And then let's see, okay, a couple other questions in the chat. I'll refer these to you here real quick. Do you want to talk a little bit about Osprey? Yeah. And you didn't open up the Osprey code.
No, I can't.
Which maybe just a high-level
sure.
piece. So Osprey is the portion of the code that does the hourly dispatch. So it's in GAMS rather than Python. So Python calls the GAMS code that does the dispatch because it's solving an optimization problem to do the dispatch. So I don't know that we want to go into much more detail than it may be helpful, Will, just to show where it's at in there.
Yeah, I will show just very quickly. So I'll share my screen and I'll just keep sharing.
And then Pat, and then you're welcome to follow up if you have other questions beyond there.
Okay.
Thank you.
So, right, yeah. So once we prepare the data, which includes, as I mentioned, we're going to write out a bunch of CSV files here with available capacity, daily energy budget, net load, these types of things, and then all of these properties that are needed in the Osprey also go into a GDX file, which the reads Auger folder has this Auger data folder, and this has the reads data, which is used in Auger, and then it would also write out all of the additional CSV files and the GDX file that are going to be used in Osprey are going to be read out here. And then the next thing that happens in this main auger.py script is that we're going to run Osprey. So here's where we call the B1 Osprey GAMS file. And we give it a few switches, which change the operation based on how we're running reads. And then the next thing is we're going to call this GDX dump file. And all this GDX dump file is going to do is just going to grab the results from Osprey and write them out as CSV files. And maybe that's about as far as we want to get into Osprey right now.
And Sandra, your question about reads Auger dealing with flexible load, that as you go through and look through the Osprey constraints, you'll see some of that where we'll have daily energy budgets for different resource types, and the reads will dispatch those flexibly. So that's one way it's captured there. If you want to talk through more details, happy to take those.
Yeah, flexible load is also hinted in our hourly profiles file. We have a class for load profile, subclass of hourly profile, and one of the methods of this load profile class is adjust flex load. So this is going to adjust the hourly load profiles in Augur based on the optimal load flexibility determined by reads, if you're using ESS flexibility in reads.
Okay. Cool. Well, thanks, everybody. And again, yeah, feel free to follow up with us or to use the reads discussion page on the GitHub to add more pieces. Or if you find something that's broken or wrong, you can certainly submit an issue. So thanks, Will, for walking us through this. Much appreciated.
Yeah, of course. Hopefully it wasn't too much all at once. Hopefully some people benefit from this.
Cool. Well, thanks everybody. Have a great day.